My name is Ting Guangyu from National Taiwan University. Today, I'm going to talk about our work on evaluating security protocols that use camera-based visible light communication. So, visible light communication is a kind of optical wireless communications technology. When designing security protocols, VLC is commonly assumed to be an ideal channel that is resilient to eavesdropping, manipulation, and jamming. However, this assumption has not been carefully investigated. Our study aims to examine this assumption via real implementation and experiments. We implement a secure multi-device pairing protocol using CamCom, which is a subcategory of VLC, and we would like to share the results with you. Here's today's agenda. First, I'll briefly explain the security assumptions of VLC and CamCom commonly made by previous work. Second, I will show the experiment results and some practical considerations we observe and survey while conducting the experiments. Then, we show the preliminary results of attacking CamCom by laser light. And finally, future work and the conclusion. In general, a VLC system is constructed by two parts: the transmitter, or in other words, the light source, and the receiver. The receiver can be a camera or a photodiode. The transmitter is normally LED, and it can encode data in the frequency of its flicker or in its colors. Our scheme is based on camera communication, taking a camera as the receiver and an array of color-changing LEDs as the light source. VLC has several interesting properties that can enhance security, like directional propagation. Unlike many RF signals, VLC only propagates towards the direction where the light points, and human visibility. Not like radio frequency channels, human users can see a light source directly, so users can observe and check whether the light is transmitting as expected. Special confinement means that light cannot penetrate an obstacle, so we can easily restrict the transmitting range of a light source. Additionally, CamCom enjoys properties such as parallel channels. It can handle many light sources simultaneously as long as the camera view can accommodate them. And precise positioning. Using computer vision techniques, we can get the relative position of the transmitter. Combining the above property, CamCom is believed to enhance physical layer security in several aspects. First, physical authenticity. Combining directional propagation and human visibility, VLC data transmission is resistant to physical layer modification and impersonation. Attacks attempting to tamper with the transmission have to be within line of sight, and thus can be detected by human observers watching the VLC carrier and surroundings. Second, ease of isolation. Because visible light cannot penetrate obstacles, as mentioned in special confinement, an adversary behind the wall won't be able to eavesdrop on the VLC transmission. That is, secret exchanges via VLC can be easily isolated from potential eavesdroppers, but the secret exchanges over RF channels cannot. Third, resilience to jamming. Special confinement ensures that VLC channels are free from RF interference, and parallel channels ensures that many VLC channels can coexist in close proximity without interfering with each other. Thus, data transmitted via visible light is more robust to jamming than via radio frequency. Fourth, visually verifiable association. Precise positioning strengthens physical authenticity by allowing a user to visually associate transmitted information to the transmitting device. While physical authenticity binds the transmitted data to the physical presence of the transmitter, precise positioning binds the transmitted data to the precise physical location of the transmitter. Here are some examples of the unique properties of CamCom. On the left side, Per channel, as long as the LED light rings can fit in the camera view, they can transfer data to the camera at the same time. On the right, visually verifiable association. This is a camera view of the LED rings cut into 4 quadrants. The colored pixel not only encode transmitted information, but also indicate the physical location of the transmitting device. Now, let's get to the experiments and practical consideration. I'll briefly explain the security protocol we used in our experiments. The protocol aims to achieve secure multi-device pairing by using CamCom. Specifically, the protocol uses 2 channels, CamCom as a VOC channel and Bluetooth as an RF channel. The protocol assumes the VOC channel is authentic and uses it to protect the DP-Holman key exchange performed in the insecure RF channel. Here in algorithm 1, when the protocol starts, a server A and a client B both generate DH key pair. The server begins listening, and the client begins broadcasting its DH public key through the RF channel and its hashed public key through the VOC channel. When receiving the public key, the server verifies it with the hashed public key. Once verified, the server broadcasts its DH public key. Then both the server and client calculate a shared key for authentication. The server and client perform nonce-based authentication to ensure a common secret is computed. The pairing succeeds if both the server and client can correctly retrieve their respective nouns. Otherwise, the server will abort the connection. We take pairing time as our main evaluation matrix. A successful pairing indicates that the server completes a pairing with every client devices within a timeout of 150 seconds. Then, here's our experiment setup. We implemented a color-based CamCom scheme designed to improve throughput by taking advantage of an array of LEDs and their colors. On the left, the server side consists of a camera and a laptop. The camera is the receiver of the LED light. The laptop runs a picture decoder and a cipher calculator. On the client side, we prepare 4 client devices, each with a Raspberry Pi 3 and an LED ring. Each client has an LED ring of 16 blobs for transmitting messages. Now, the experiment's result. Here we can see the impact of Bluetooth. Since the protocol depends on both VOC and RF channels, we investigated the difference between using CamCom with a self-implemented Bluetooth channel and with an ideal Bluetooth channel which takes 0 time to transmit. The figure shows that when using a self-implemented Bluetooth channel, the pairing times have a high variance, possibly due to interference on the same frequency band and a non-optimized Bluetooth implementation. In other words, though CamCom could scale to multiple devices, the RF channel may quickly become a bottleneck. To focus on one factor at a time, we consider the ideal Bluetooth channel for the rest of the experiments. The second figure shows the average pairing time at different distance from 1 to 4 LED rings, revealing a similar trend of different numbers of rings. Particularly, as the devices move away from the server, the average pairing times for the different numbers of rings are equally low. Within our test range, we can see that the impact of distance is not as critical as we imagine. Last but not least, surprisingly, we found that the pairing time is the shortest in average when an infinite focal length is set. Further investigation suggests that although an infinite focal length blurs the captured images, the blur increases the area of the colored pixels, which in turn help the decoding process of our color-based CamCom scheme. Now, let's talk about some practical considerations we encountered and might encounter when implementing CamCom for security protocols. We classify them into 3 categories: hardware, software and configuration, and environment. Factors in the first category can only be overcome by replacing the hardware, whereas factors in the second can be changed by updating the software code or configuration. The third category may be changed by adjusting the environment. Frame per second and RF hardware are 2 main considerations of hardware. For FPS, since CamCom uses a camera as the receiver, the throughput is bound by the camera's frame rate. If the transmitter changes color or blinks faster than the camera's FPS, the receiver will be unable to collect correct image to decode the messages. Next category is software and configuration. On the transmitter side, such as frequency of message transmission. While FPS defines the speed of data reception, the frequency of transmission focuses on the speed of data transmissions on the transmitter side. Since using a light bulb can blink or change color faster than the FPS rate, we need to programmably control the rate of the lighting change, such that the receiver can reliably capture all encoded data. Or on the receiver side, for instance, number of devices per camera view. In our VOC setting, each camera has a fixed dimension of view for capturing images. If we increase the number of devices that can fit in the camera's view without adjusting the distance, the space between the devices must be decreased. If the lighting sources of the device are too close to each other, the receiver may have trouble decoding individual transmitted messages due to scattered light interference. Finally, the third category, environment. Ambient light such as sun or unintended light sources in the same indoor environment is one of the main challenges to visible light communication. Or obstacle. Since visible light travels in straight lines, any obstacles between the transmitter and the receiver would interfere with the data transmission. Please check out our paper for detailed discussion about each of these factors. So far, we have examined CamCom-based security protocols in non-adversarial setting. We are also curious about whether and what an active attacker can do to break CamCom-based security protocols. To experimentally simulate what an adversary might do, we use a laser pen to emit red light as an external light source. As these figures show, we experiment 2 kinds of attacks. One is emitting light at the LED rings, one is from behind the LED rings. Interesting, we found that while the left one can be an effective denial of service attack, the right one is not as effective as we thought. The decoded message is still intact. This is probably due to how our decoding algorithm works. The server could still differentiate whether the external light is on the ring or not, and we only decoded the light which is on the ring. To wrap things up, CamCom presents new opportunities for security applications. However, we show that when implementing CamCom for security protocols, certain limitations and trade-offs could potentially degrade the expected performance and security. For future work, we plan to investigate attacks that interfere with CamCom directly on the physical layer and explore CamCom schemes that are robust against such attacks. We hope our result can be a first step toward understanding the realistic behaviors of CamCom. We believe more work is needed to help researchers make realistic assumptions when adopting CamCom for security applications. Thank you for your listening.